Good day. This is MEG 224 Engineering Mechanics 2 Dynamics, Lesson 9, Plane Kinetics of Rigid Body, Principle of Impulse and Momentum, Part B, which can be found in Chapter 19 of Engineering Mechanics Dynamics by R.C. Hibella. Lecture objectives: to apply the principles of linear and angular impulse and momentum to solve rigid body planar kinetics problem that involve force, velocity, and time, to discuss application of conservation of momentum, principle of impulse and momentum. The principle of impulse and momentum for a rigid body can be developed by combining the equation of motion with kinematics. The resulting equation will yield a direct solution to problems involving force, velocity, and time. Principle of linear impulse and momentum. The equation of translational motion for a rigid body can be written as summation F is equal to mag, and A is acceleration of the mass center, so which is the V dt. So since the mass of the body is constant, summation F can be d dt of mvg. So multiplying both sides by dt and integrating from t is equal to t1 when vg is equal to vg1 to t is equal to t2 when vg is equal to vg2 yields integral summation of integral f dt is equal to mvg2 minus vg1. So this above equation is referred to as the principle of linear impulse and momentum. It states that the sum of all the impulses created by the external force system, which acts on the body during the time interval t to t1 to t2, is equal to the change in the linear momentum of the body during this time interval shown in the figure. So this is the initial momentum, then plus all the impulses will give us the final momentum. Principle of angular impulse and momentum. If the body has general plane motion, then summation mg is equal to ig alpha, which is equal to ig the omega dt. Since the moment of inertia is constant for that particular body, summation mg is equal to d dt of ig omega. Multiplying both sides by dt and integrating from t is equal to t1 when omega is equal to omega 1 to t is equal to t2 when omega is equal to omega 2 gives integral mg dt, which is ig omega 2 minus ig omega 1. In a similar manner, for rotation about a fixed axis passing through the point O, summation m naught, that is moment about the point O, is I naught alpha. When integrated, becomes summation m naught dt from t1 to t2 is equal to I naught omega 2 minus I naught omega 1. This equation referred to as the principle of angular impulse and momentum. Both equations state that the sum of the angular impulse, the sum of angular impulses acting on the body during the time interval t1 to t2 is equal to the change in the body's angular momentum during the time interval. So to summarize this concept, if motion occurs in the xy plane, the following three scalar equations can be written to describe the planar motion of the body. That is mvgx1 is plus summation of fx dt from t1 to t2 is equal to mgx2. So likewise for y direction, then this is the angular momentum. So the term in these equations can be shown graphically by drawing a set of impulse and momentum diagrams for the body as shown in the figure. Now, the linear momentum, mvg, is applied at the body's mass center. So figures A and C, whereas the angular momentum Ig omega is a free vector, and therefore, like a couple moment, it can be applied at any point on the body. When the impulse diagram is concentrated or is constructed as shown in figure B, the forces F and moment L vary with time and are indicated by their integrals. So, however, if F and M, that is the force and moment, are constant, the integration of the impulse yields F into T2 minus T1, and the M is into T2 minus T1 respectively. Such is the case for the body's weight. The three equations stated above can also be applied to an entire system of connected bodies rather than to each body separately. This eliminates the need to include interaction impulses, which occur at the connections since they are internal to the system. The resultant equations may be written in symbolic form as this. That's the first one is for x direction, system linear momentum initial plus the system linear impulse complete, which is equal to system linear momentum final. Likewise for y direction, this is for y direction, and this is angular momentum. So as indicated by the third equation, the system angular momentum and angular impulse must be computed with respect to the same reference point O for all the bodies of the system. Conservation of momentum. Conservation of linear momentum. If the sum of all the linear momentum, linear impulses acting on a system of connected rigid bodies is zero in a specific direction, then the linear momentum of the system is constant and conserved. So, the summation of system linear momentum, the initial momentum is equal to the summation of the system linear momentum final. So, this equation is referred to as conservation of linear momentum because there are no impulses. So without inducing appreciable error in the calculation, it may be possible to apply the equation above in specified direction for which the linear impulses are small or non-impulsive. Specifically, non-impulsive forces occur when small forces act over a very short period of time. Typical examples include the force of a slightly deformed spring, the initial contact force with a soft ground, and in some cases, the weight of the body. Conservation of angular momentum. Angular momentum of a system of connected rigid bodies is conserved about the system's center of mass, G, or a fixed point. When the sum of all the angular impulses about this point is zero or appreciably small, the third of the equations, this Bm becomes, because the angular impulse is gone. So this equation is referred to as the conservation of angular momentum. In this case, of a single rigid body, if applied to point G, becomes Ig omega 1 is equal to Ig omega 2. For example, consider a swimmer who executes a somersault after jumping off a diving board. So by tucking his arms and legs in close to his chest, he decreases his body's moment of inertia and thus increases his angular velocity. Ig must be constant. If he straightens out just before entering the water, his body moment of inertia is increased, and so his angular velocity decreases. Since the weight of his body creates a linear impulse during the time of motion, this example also illustrates how the angular momentum of a body can be conserved, and yet linear momentum is not. So, such cases occur when the external forces creating the linear impulse pass through either the center of mass of the body or the axis fixed axis of rotation. So now let's look at an example as a tutorial. So 100 kg spool shown in figure A has a radius of gyration K of 0.35 meters. A cable is wrapped around the central hub of the spool, and a horizontal force having a variable magnitude of P is equal to T plus 10 Newton is applied, where T is in seconds. So this is the rope that was applied. So if the spool is initially at rest, at T is equal to 0, then every other thing is 0. So determine the angular velocity in 5 seconds. So omega 1 is 0. So assume the spool rose without slipping at point A. This is point A. Then the solution said we have to first of all look at the free body diagram. And then said the free body diagram, figure B, the variable force P causes the friction Fa to be variable too. And thus, the impulse created by both P and F must be determined by integration. Since P is what is causing the wheel to roll, then that is what is going to cause the friction, because the friction is due to the rolling. So for P, force P causes the mass center to have a velocity Vg to the right. So the spool has a clockwise angular velocity. So principle of impulse and momentum. A direct solution of omega can be obtained by applying the principle of angular impulse and angular momentum about point A, that is the Saturnal center, in order to eliminate the unknown friction impulse. So we say that initial momentum plus, initial momentum plus plus the impulse is final momentum. So this is from 0 to 5. Then the distance here is 0.5, 0.75 plus 4, because from here to here is 0.4. Then from here to here is 0.75. Of course, if this string or rope had been here, it would have been 1.5, which is the diameter. So, which is equal to mk square. This is mass times radius of gyration with 100 times 0.75, then all of them omega square. So this gives you the moment of inertia. So then 6.85 omega 2 is this. Then you can find omega 2 to be 1.05 radians per second. This problem can be solved by applying the principle of impulse and momentum about G and using the principle of linear impulse and momentum in the x direction. Thank you. This is part B. And do not forget to like my video, subscribe to my channel, share, press the notification bell for new videos. And if you are one of my university undergraduate students, please do not forget to subscribe with your real name. And thank you. God bless.